Now we're going to go over question 9, which is a disjoint set or union find problem. And so first it starts by defining a union find node implementation. And so this is using sort of the tree-based representation, right, where we have pointers and nodes, and we see that we have a parent or null, which is null if I am the representative node of the set, and then also has the node's value itself. And then we see that there are these two methods, find and union, which are not actually shown for the implementations, but these are the basically standard parts of the union find interface. Or I guess here it's a class, but right, it's implementing the union find or disjoint set interface, which says that we need to be able to find and union things. Cool. So the first part says, hey, if we aren't careful in implementing the union operation, it's possible to end up with a very spindly union find structure that looks like this, or in other words, like a linked list. However, assuming we use path compression, how long will it take in the worst case to execute n find operations where all of the x's are in this one set? Well, let's sort of play around with this and look at all the possible combinations of find operations we could do. Well, what if, let's say, we started by doing find on the last element? If we started there, then what we would see is that after path compression, everything on this path, which is all the items in the union find, would have their parent set directly to be the representative of the set, right? Because path compression says that rather than having a whole chain, once we know who the parent or the representative of the set is, we'll just set your parent directly to be that. And so if we were to call find on n, we would see that it actually results in a really flat, awesome structure like this. And now all subsequent find calls take constant time. All this required was that we had that first call at the beginning that took linear time because we had to traverse all the way from the bottom to the top, but everything after that is constant, no matter what you do. Okay, cool. What if we maybe started at the other end and we only started by doing find on, I don't know, an element towards the beginning, right? Well, we see that if we call find on 1, that's going to be constant, right? It doesn't really change anything. And if we did that n times, then it would in total take n work because every single time it's constant. Okay, no problem. But what if we called it, let's say, on 2 and then 3 and then 4 and then whatever? Well, what we're going to see is that because of path compression, even if we looked like this at first, if we called it on 2, great, that's near constant. If we called it on 3, okay, sure, that takes 2 steps. But after that, our subsequent paths are a little shorter. And so if I were to union find on the next element, well, that still only takes 2 steps. Okay. And no matter what I do, I see that even if, let's say, I have all this, right? And then I do, I'm going to skip all the way to n. Well, not only is the path a little shorter, but then again, we have the whole thing where after calling union find once on n, every subsequent call is going to be constant because of the path compression, right? And so we see that basically calling find on an element really late in the set results in one initial call that takes linear time, and then many calls after that that take constant time each, so roughly linear time total. Or if we were to do the opposite and call find on elements towards the beginning or higher up in the tree, well, then each of those calls is short and takes very little time. And subsequent calls might take a little longer, but they all result in the path compression. And so what we're taking away from this is that we're basically limited in total n time, right? Because the longest, hardest operation, right, the hardest find, which would be calling find on the latest element, can only happen once, right? We can't have like n squared behavior because once we do the call on find n that takes n work, every call after that is constant. And on the other extreme, once again, we see that, okay, we could do a lot of calls that are really little, but then that's still total linear time because we're doing n calls that each take very little time themselves. And so we see there's this balancing between, basically there's just a limit, which is that you can't do a really expensive call many times because doing that expensive call once results in path compression, which saves us from doing it again. So we're limited, and overall this takes n or linear time. Then problem B is basically a mechanical quick find or union find question, which says, to get optimal results, union should use path compression and always arrange so that the representative of the resulting structure is the representative of the tree that had the larger height after path compression. So let's show the union find structure that results if we perform basically unioning 6 and 10. And so what's going to happen? Well, first, if we're unioning 6 and 10, we're gonna call find on 6 and 10 to find their representatives, right? Because not only do we need to make sure that they're not already connected, but also we need to just know the representatives so we can connect the representatives, right? Because that's how the union find structure works. And so calling find on 6, because of path compression, results in a tree that looks like this, right? This path is unchanged on the left, but all of these nodes along this path get compressed. And so we result in 2, 5, 6. Okay, great. What about this neighbor? This union find, right? Well, we see all of these get compressed, this path from 10 to the root. And so what we're going to have here is 7, 12, 8, and then we see 9 is compressed, right? I'll put 9 right here. And 10 is also compressed. And then 9 had that child 11. But we see that 8, 9, and 10 are all now directly pointing to the parent because of path compression. And so these are the resulting paths just after finding the 2 representatives. And now after path compression, we are going to take the tree with the larger height and make that one the parent or the representative, which means this tree, which is taller, becomes the set representative. And so 7 becomes 0's child. And that's it. Good job.